What if we take it up a notch? What if we have a voltage source that's an alternating voltage and a capacitor? Okay. The math here is actually interesting. You should look through this. Remember, the charge at any time on a capacitor is the capacitance times voltage. Capacitance is how much charge we can store per unit volt. And voltage is right here. So our current is the derivative, this is just definition of current, derivative of charge per unit time. Plugging all this in, we get this formula here for current that is a shifted version of the voltage. So voltage went like sine, current goes like cosine. And remember, sine and cosine are the same graph, they're just shifted over by pi over 2. So we get an out of phase current and voltage. So every book I've ever taught out of draws a graph like this. I've never liked this. These two graphs really don't belong on the same picture. They have different units. This guy's measured in amps, this guy's measured in volts. So putting them on top of each other, we're kind of abusing notation here. The point of this picture is to show you that the voltage and current are out of phase. Don't look at this and think, oh, the voltage is bigger than the current. These have two different units. This guy's measured in volts. This guy's measured in amps. The point of this picture is that we say the current leads the voltage. You reach maximum current 1/4 of a cycle before you reach maximum voltage. And those two are related by this formula here. This is one we want to write down. So I'm going to write it in a different version. I'm going to write it like Ohm's law. So this is V equals I chi C, where this is called the capacitive reactance. In this scenario, when we just have this voltage source and a capacitor, the capacitor kind of acts like a resistor using this quantity where chi C equals, and I don't have this memorized either, you don't have to memorize this formula, 1 over omega C. So this is in ohms. So this really just looks like Ohm's law. This is our peak current. Same thing for RMS. I could replace my VP and VI with the RMS values. Okay, so omega is the angular frequency. It's how fast our voltage source is oscillating in radians per second. C is the capacitance of that capacitor. So the stronger the capacitor, the weaker this chi C is. So the less this thing will act like a resistor. Okay, what if we only have an inductor? Okay, similar math here, only we get this really cool differential equation. You guys have to take DE at some point, I'm sure, right? This isn't even that hard of a DE to solve, but we've got this oscillating voltage source that we're assuming goes like a sine value, and we've got an inductor in here. Remember, inductors, the whole point of an inductor is they try to stop changes in current. So as this voltage is increasing, this guy is acting like a resistor. When this voltage is decreasing, this guy doesn't like that change, and it tries to act like a new current source. It'll induce a new EMF. It tries to undo whatever this guy's doing. So here's all the math. The induced EMF, we know is negative L di dt. That gives us this differential equation here. And we want to solve that for I. We get this formula. Notice instead of a plus pi over 2, we get a minus pi over 2 here. So again, my current and voltage are out of phase, but now the voltage leads the current. I reach maximum voltage 1/4 of a cycle before I reach maximum current. So when I'm saying that, remember Hertz is our frequency, and there's a relationship between F and T and omega. We have all those formulas written down. So one entire period is from here to here. Our frequency is how many periods we do per second. 1/4 of that period is the time interval between when we reach maximum voltage and maximum current. And those are related, the voltage peak, not instantaneous. See right here, at that moment, we're at maximum voltage. My current is 0 at that moment. What we're comparing here are this maximum voltage and maximum current. They're related by this equation, which is Vp equals IP chi L. Again, it looks like Ohm's law. V equals IR. This guy here is called the inductive reactance. And chi L equals, again, I don't have this memorized. I think it's omega L. Yes. Where L is the inductance of that inductor, and omega is our angular frequency. So again, this is in ohms. This is the alternating current version of a different kind of resistant element.